We've mentioned in the past that solubility is the ability to dissolve in water. And so now in these next couple videos, we're going to look at what's actually happening when something dissolves in water. Rule number 1 of solubility is that like dissolves like. And by that we mean that polar molecules can dissolve in polar solvents and nonpolar molecules will dissolve in nonpolar solvents. Like dissolves like. So we have to think back to the days of Lewis structures, polar molecules, nonpolar molecules, and of all solvents, by far water is the most common. It's the one that we'll usually work with. So if I remember the Lewis structure of a water molecule, the center oxygen has 6 valence electrons, 2 pairs, 2 singles, and then we hook on the hydrogen. 1, hydrogen 2. Connect the dots. That's an H. There we go. We said that this is a bent structure. The 2 hydrogens are not coming off at equal angles because of those lone electron pairs on the oxygen. We also mentioned that this is a polar molecule. Polar molecule. Polar meaning that there's an end that's a little negative and there's an end that's a little positive. The oxygen end of the water molecule carries that partial negative charge. Number 1, there's 2 lone pair of electrons and electrons are negative. Number 2, the oxygen-hydrogen bond is very polar, with oxygen having a higher electronegativity. So these electrons that are being shared are drawn closer to the oxygen, making that oxygen region partially negative. That leaves the hydrogens as partially positive. All right, so that's what it means to be a polar molecule. There's a region that's partially negative and a region that's partially positive. With water being our most common solvent, we'll definitely need to know that water is a polar molecule. So other polar molecules will dissolve in water. Some of the most polar molecules are the ionics. Ionic compounds are like as polar as it gets. For example, sodium chloride. Sodium chloride. We can kind of draw a Lewis structure that sodium only has 1 valence electron. Chlorine has 7. We can link them up. Here's the bond. Now if we wanted to be a little more specific, they're not sharing that electron pair. The electron pair in the center here completely belongs to chlorine. Sodium will donate its 1 valence electron so that the chlorine isn't just partially negative, it's a full out -1. The sodium is a full-blown +1. But since we have regions of charge, positive and negative, ionics are very polar. This is definitely a polar molecule. Ionic compounds often dissolve in water very well because the sodium, which is positive, will be attracted to the negative oxygen end of the water molecule, and the negative chlorine will be attracted to the positive hydrogen end of the water molecule. Those attractive charges and forces will help these particles interact and dissolve. So some of the examples that they're giving me in these pictures, we all know water and oil don't mix. Water and oil are not soluble. And now I know that the water is a polar molecule. So even though they're not telling me like the chemical structure of an oil molecule, I could at least tell you that the oil is nonpolar. Because water and oil are not soluble. They do not mix. Like dissolves like. These guys must be opposites. I know water is polar, so the oil must be nonpolar. This center picture, they're trying to show that the water and the rubbing alcohol do mix. They are soluble. They also kind of give me the formula of that alcohol molecule. It looks kind of like this. We'd have 3 carbons, single bonded. They will be surrounded by 7 hydrogens. 6, 7. And then the last spot belongs to that OH group. And now this is really similar to the water molecule, where the oxygen, I mean, it really does have those 2 lone pairs. Suppose we could draw them in. To prove that the oxygen has an octet, it's a very polar bond here between the hydrogen and the oxygen. So the oxygen will be slightly negative, the hydrogen slightly positive. This region here of the alcohol molecule will be very attracted to a water molecule. Now the carbon region over on the opposite end, this part of the molecule is pretty nonpolar and really won't interact a whole lot with the water molecules. It'll be that OH group on the alcohol that's very attracted to water molecules. This is a polar molecule. There's a region of partial positive and a region of partial negative. These two will be soluble. The water, I know, is polar, and so is the alcohol. Now, even without giving me the structure, so I could kind of draw the Lewis structure, if I knew that water and alcohol are soluble, that they mix well, then I could tell you that the alcohol is polar, because like dissolves like. The last picture, they're trying to show that oil and dry cleaning fluid are soluble. They mix well together. And so if I know that the oil is nonpolar, because the oil does not dissolve in water, nonpolar, I could tell you that the dry cleaning fluid must also be nonpolar. If these two mix, like dissolves like. So I could tell you also then that dry cleaning fluid probably is not soluble in water. So they could do this on a test question, kind of inferring about the solubility of a compound. Water is the most common solvent. So if I knew that water was polar, then oil must be nonpolar. And then if they told me that oil and dry cleaning fluid do mix, I could tell you then that these must have the same polarity. Both nonpolar in this case. And they do kind of give me the formula, so I could sketch a little structure. Tetrachloroethylene has 2 carbons. They're double bonded. And then each will have a chlorine. I should say 2 chlorine, kind of coming off at an angle. You will not need to draw Lewis structures for the solution test, but sometimes it's kind of helpful to kind of know where we're coming from, that why do these mix or not mix. That this is a non-polar molecule. If you look at each carbon and really the entire structure, the chlorine are evenly distributed around the center carbons. This would be a non-polar molecule, which is why it would not mix with water. And it does mix with oil. So again, you don't need to draw Lewis structures. It's kind of helpful to remember the Lewis structure of water. But then in the next couple videos, we'll kind of look at what's happening on a particle level when, say, an ionic does dissolve in water. Or what about like dissolving like, nonpolar mixing with nonpolar. But for now, this is good. Water being by far my most common solvent, and like dissolves like.